Let us now talk about asymptotic analysis. This is the analysis that we do most of the time. Whenever we talk about analysis of algorithms, we talk about asymptotic analysis only. The terms like theta notation, big O notation that you hear a lot, all these terms are related to asymptotic analysis only, and they are called asymptotic notations. The thing about asymptotic analysis is we measure order of growth of time taken by a function or program in terms of input size. For example, if input size is n or input value is n, does your program grow quadratically, linearly, is it constant, or any polynomial function it has, right? We check that part only. How is the time taken growing in terms of input size? That's what we measure in asymptotic analysis. We'll get a very clear idea when we'll do some examples. The thing about asymptotic analysis, the best part about asymptotic analysis is does not depend upon the programming language, does not depend upon the machine, and does not depend upon the test cases also. We talk about worst case analysis most of the time, and that's algorithm specific, not test case specific. One more thing about asymptotic analysis, you don't have to implement the algorithms, right? You have an idea, you write the steps, then you can analyze it. Is it worth implementing it, right? You don't have to implement like we implemented 3 different approaches. We could just write the idea of 3 different approaches or write the algorithms for 3 different approaches, and we could analyze them using asymptotic analysis. We do not have to implement and then measure the time. Let's now get an idea about asymptotic analysis. So what we do in asymptotic analysis is, the first thing that we do is we get an expression of time taken by your code in terms of input size. So let's understand this with the same examples that we wrote earlier. This is a first way of writing the code to find the sum of first and natural numbers. We are using a direct formula here. So what are we doing in this function is, we are doing an addition, we are doing a multiplication, and then we are doing a division, right? So if you consider these 3 operations independently, you are basically doing 3 operations. And we always assume that a mathematical operation or a comparison operation or any type of operation always takes constant time irrespective of input value. Whether you add 1 million to 1 million or you add 10 to 1 or 5 to 1, they are assumed to be taking the same time in asymptotic analysis, right? So what we are saying is, we are doing 3 operations, and all these 3 operations take the constant time irrespective of input value. So that is why we have written the time taken as C1 here. Let's now see the second function. In this function, we are running a loop from 1 to n, and then we are doing sum equal to sum plus I. So this expression is happening n times, right? And then there are certain expressions that are happening only once. For example, this sum equal to 0 is happening once. This initialization of I equal to 1 is happening only once. This return sum is happening once. So there are some things which are being executed constant number of times, and some things which are being executed n times. So that is why we have written the time taken as C2n plus C3. Now one interesting thing is, even if it is not exactly n times, even if I write this as say less than n or say less than n minus 5, even in those cases I can write the time taken as C2n plus C3. Why? Because say if I write n minus 5 times with some C1 and then say some C2, I can rewrite this as with new constants say C6 and C7, then I can write as C6 n plus C7, right? Now C6 is same as C1 and C7 is C2 minus 5C1, right? So even if you have less than sign or you have n by 2, n by 3, it's all can be written as C2n plus C3. If you have n by 2 or n by 3, then your C6 becomes C1 by 2, right? So as long as you have an expression in terms of n here, you can always use C2n plus C3 for such loops, right? So this function is going to take this much time. Let's now see our third example. In this example, we have this expression which is being executed n into n plus 1 by 2. What are we doing in this logic? We are incrementing sum these many times. So we are ultimately getting the same value here, right? So if I try to compute how many times this expression is being evaluated, I get n square by 2 plus n by 2, right? This is what I get. So those many times this expression is being evaluated, and then there are some other expressions which are being evaluated different number of times. For example, this is being evaluated once, so this is also being evaluated once. This is being evaluated n times, right? Because this j equal to 1 initialization happens for every value of I. So overall, I can write it as C4n square plus C5n plus C6. There are certain things which are happening constant, which are taking constant time, certain things which are happening quadratic, certain things which are happening linear number of times. So that's the expression for time taken by this function fun3. So we got expressions of time taken for all three functions, fun1, fun1 and fun2 and fun3. See here I have written the time taken for actual implementations. I have written the codes which work in C, C++ and Java, all the languages. But we don't have to implement. We can write the algorithm also and analyze the algorithm as well, right? Now, time taken we got in these forms. Let's get an idea of order of growth as well. So how are these time taken helpful to figure out order of growth? See, to give you a quick answer, what are we going to do in the order of growth is, we are simply going to take the leading term of every expression. We are going to say it's constant order of growth, does not depend upon n, it's linear and it's quadratic, right? We'll talk about formal definition of order of growth and how did I say constant, linear and quadratic later. But a simple rule is you can always ignore the lower order terms, right? And you can say this is what the order of growth is. For example, here there are three terms. I can ignore these two and I can say it's quadratic, right? That's the simple idea. We'll talk about that later. Let's now get the understanding of order of growth, how these expressions help us. So let's take some example values. Let's say you are the one who wrote this efficient code and your friend wrote this inefficient code, right? And you ran it on a machine where the value of C1 is 13, right? You ran it on a slow machine where it takes 13 units of time to do this work, this constant amount of work, or you can say C1 is 13 for your machine, right? Now your friend ran it on a different machine which is slightly faster, and for him say C2 is 2 and C3 is 5, right? So your friend got the expression 2n plus 5 for time taken and you have the expression as 13, right? So what happens with these two machines and these two functions when you run them, and I'm assuming that every time you run them they are going to have the same constants, the machine load does not change, right? So what happens in time taken is your machine's time is always going to be 13, right? It's constant value. Fun1, your function, it's always going to take 13 units of time on your machine. Your friend's time taken depends upon n. So it's going to be taking for n equal to 1, it's going to take 7. For n equal to 0, it's going to take 5. For n equal to 3, you can put the value and you can get. And if I find the intersection point of these two functions, I can get the intersection point as 4, right? 13 equal to 2n plus 5. And I get the n as 4, right? So this is what the value of this intersection point is. Now if you take a look at this intersection point, what happens is after this intersection point your friend's function is always going to take the more time, right? Even if your friend chose a faster machine, had a faster machine than you, and you had written your code fast but your machine was slower, but after value of 4 your friend's code is always going to take more time than you. That's the beauty of order of growth. Because the order of growth of this function is higher and this function is lower, it's constant and it's linear, right? The machine specific things go away, right, after the value of 4. Now even if you choose a further slower machine, say you have n equal to 1000 and your friend has even lower values, even in those cases there would be a value of n after which this expression, because this is growing with n, right, and this is constant, so there would be a value of n after which this expression will have more value than your value. Here I have redrawn the graph for different constant values. Say this time you got even a slower machine. You had to run your logic, your fun1 function that you wrote on a mobile phone, and your friend got even a faster machine. So the constants for you are 1000 and constant for your friends are say 1 and 1. So the value of the function fun2, the time taken for fun2 is n plus 1, because the friend is running on even a faster machine, and for you it's only it's high value, it's 1000, right? You got a mobile phone now. Now your friend says that my program is taking less time. Now how do you prove that your program is faster? So the asymptotic analysis works here as well. What is going to happen is there is going to be a value of n after which your friend's program is always going to take more time. It's just that the value of n is higher this time because you have a slower machine, your friend has a faster machine. So if I compare these two functions, n plus 1 and 1000, and if I say give me the values for n for which I have higher value of this expression, I get the value of n as 999. After 999, and 999 is this point, after this value, the fun1 is always going to take more time than fun2, right? The fun1 is always going to take more time. You can put the values. It's going to be 1000, 1001, 1002, and 1003, and so on. So that's what the great thing about asymptotic analysis and asymptotic notations are. We are going to see mathematically also why it is true that if something is having higher order of growth, then that thing always have higher value after certain value of n. We'll discuss that. How is it mathematically true? Before we end this video, let's quickly talk about fun3 also. Fun3 is a quadratic function, right? And quadratic functions grow even faster. So quadratic functions grow like this, right? So fun3 is going to have a value again, after which it's going to take more time than even fun1 and fun2. Before we end this video, let's quickly talk about fun3 also. Fun3 is a quadratic function. So it's going to have a graph like this, right? A quadratic growing graph. And you can notice that after a certain point, fun3 is having more time than fun1. And if I compare it with fun2, then the way I've chosen the constants here, drawn the graph here, it's having higher value than fun2 all the time, right? One last thing about asymptotic analysis and this graph, we are always going to be considering this quadrant of the 2D coordinate system, because the time taken by an algorithm cannot be negative, right? It is either 0 or growing with the value of n. And n is typically size of input, right? And this value of size is always going to be 0 or greater than 0. So whenever we draw the graph or whenever we talk about asymptotic functions, asymptotic analysis, see, these are the functions of time taken, right? They show you how much time taken by fun2 and how much time taken by fun1, right? So they are always going to have a value greater than or equal to 0. Same is the case for input size n.